Welcome back. In this lesson, we're going to talk about energy and how we use it, where we get it, and how we use it. Where we get most of our energy right now is fossil fuels. Think of fossil fuels sort of as stored solar energy because plants get their food from the sun and they generate glucose, and then eventually those turn into fossil fuels. This is the American viewpoint. The Russian viewpoint is that petroleum and natural gas are made within the earth themselves, so that they're not necessarily fossil fuels. So this this theory may change, and us Americans may start to go along with the Russian viewpoint. But for right now, this is the accepted science that fossil fuels are from previously living matter. And oil is a heterogeneous mixture, and there's two main types of oil. There's light crude and heavy crude. When you hear about oil, usually people are talking about light crude. There's also quite a bit of heavy crude in Venezuela and in Canada. So just some definitions about energy and power. Energy is the ability to do work, and a couple different forms: heat, kinetic energy, potential energy. And power is energy divided by time. So power is the rate. So compare it to something like a Ford Focus versus a Corvette. So they both weigh about the same. So when those cars are going 60 miles per hour, they have the same kinetic energy because they have the same mass. But a Corvette can get to 60 miles per hour faster. That's energy divided by time. A Corvette has more power. That's the difference between power and energy. And fuel, what is a fuel? Fuel is something that has stored energy. It's a reduced form of matter. And as the fuel is combusted, that's the most common thing, that the potential energy goes down, meaning that the potential energy is high in the fuel, and after it's burned, carbon dioxide and water, the energy of that is lower. So this change in energy, that's what's released. And this goes with the laws of thermodynamics. First law is a conservation of energy. So the idea is that change of potential energy is equal, that change energy is the energy that's released. Second law is entropy, and we talked about this before, that a higher entropy means more disorder. And this makes things like perpetual motion impossible because things will always reach more and more disordered, and then eventually things will stop. Now, I showed you this picture previously. This is a picture of me in Las Vegas in the Mars candy factory here, and I like this for entropy because these M&Ms, these are all very ordered, very separated. This is very low entropy. These M&Ms over here are in high states of disorder. Those are high entropy. So petroleum is the basis of our chemical industry right now, and it's really easy to work with. Why? It's a liquid. We can pump it right from the ground. Compared to coal is a solid. We have to mine it. It's a little more difficult. But petroleum, also natural gas, you can pump them right from the ground. And the idea is that there's a rock called a capping rock that oil cannot penetrate through, so it traps the oil. And petroleum by itself is not particularly useful, but we can take petroleum and we can turn it into more useful things like gasoline or plastic or asphalt for our roads, but we use it mostly for fuels. And the most common way we make petroleum more useful is by distillation. But we can also crack things. So what cracking is when you have a long molecule, you can crack it, break it up into smaller molecules, and those are more useful. For instance, a molecule like that would make up asphalt is a very low value product, but then if you can take the asphalt and turn it into diesel fuel, that's a much more higher value product and get more money for it. Also, certain alkanes and alkenes can be reformed, meaning they change shapes of the molecules to make them more useful, to make them better fuels. And here, this is a picture showing the different types of traps. This trap right here. This is a normal trap, and you can see this dark brown rock is the capping rock, and the green is the oil and the natural gas. And this is how most traps are like this. Here's another common one. This is called a fault trap. Down here, this is a salt trap. You find these more often in the ocean in the Gulf of Mexico as well. So Gulf of Mexico has quite a bit of these salt traps down here. And the idea is you drill down and you want to aim slightly, slightly to the edge of the natural gas and oil because the natural gas on the top, and then natural gas can put pressure on it, and then the oil can shoot up. That's also known as a gusher or a geyser when the oil can just squirt up. That happens from natural gas pushing it up. That's what the geologists target when they drill for oil. Now this is shows a distillation column, and the idea is you separate things by heating, similar to the way that whiskey and vodka and other spirits are made. But the difference between whiskey and petroleum is that there's only two outputs in whiskey. You have the stuff coming at the top, and you have the water in the bottoms. In a distillation column for petroleum, you have a bunch of different products, and you throw the petroleum in here, and the stuff that comes up the top, there's actually one missing here. This would be the natural gases. That's actually here in Hawaii. We don't have any natural gas. The gas that we use, the natural gas, is actually blowover from our distillation columns. And there's petroleum gas here, also known as naphtha or petroleum ethers. These are more often added to fuels to prevent fuel line freeze-up. And over here, gasoline. This is the primary thing we look for. And other things, so this is kerosene. That's used as jet fuel. Fuel oil, that's used to power ships and trains. Lubricants, that's like motor oil. And asphalt, this is stuff that's really heavy. We use that to make our roads. And this is something the government published showing where the cost of fuel come from. And you can see this is old data. But the point of this is that the highest level of cost does come from, in fact, the crude oil itself. And the other costs, taxes there's a moderate amount from taxes, but the biggest contributing factor is the crude oil. Oil can be taken from other sources. For instance, oil shale. Oil shale is a sedimentary rock. We have quite a bit of this in the United States. And tar sands, it's heavy crude that's in sand, and Canada has quite a bit of that. We can make gasoline from things other than petroleum. Germany did this extensively during World War II. One of the ways that the Allies tried to get Germany doesn't have very much oil, so tried to starve Hitler with his by not allowing petroleum to get into Germany. So Germany at the time was the most technologically advanced country in the world, and they generated their own fuels by synthetic means. And South Africa does the same thing today. The world tried to do the same thing in South Africa with apartheid, cut off oil, had an oil embargo. So South Africa used the technology from the 1920s that was available in Germany to make their own fuel, and they do that today. So South Africa is energy independent. They run off of coal and oil, coal and natural gas to use all their transportation fuels. Gasoline can be made from biomass or ethanol as well, but there's controversy about this, about the effectiveness of these processes. It depends on, we'll talk about this later, but it depends on how big your box is. If you just look at the distillation column, it appears to be energy positive, but if you look at growing the corn, the energy it takes to plant the corn, to fertilize it, to harvest it, it appears to be energy negative. So it depends on how big you want to make your box. Here are the oil shale deposits here across the United States, and we have quite a bit of oil shale here in the United States. We can also get more oil out of our wells by a technique called enhanced oil recovery. This is where carbon dioxide is injected in the ground, and more petroleum can be obtained from the wells. Also, there's enhanced gas recovery. You can do that for natural gas as well. The United States and Canada, we have a lot of potential for this. For us in the United States, we have access to 240 billion barrels of oil from this. Saudi Arabia has 260 billion barrels, so that's quite a bit of oil we have available from that. So with oil pollution, there's oil spills, affects marine life. Petroleum in general is toxic and extremely smelly. You don't really want to get it on you. Maybe you've studied from American Revolution with the tarring and feathering of people. It was not a very pleasant thing to have happen. The worst oil spill in history was during the first Gulf War. Saddam Hussein dumped a bunch of petroleum into the Persian Gulf to try and prevent Allied ships from entering the Gulf. This oil spill is even worse than the oil spill that happened in the Gulf of Mexico. That is not the worst oil spill in history. The worst oil spill in history is without a doubt from Saddam Hussein in the first Gulf War. Moving on to natural gas. Natural gas is a mixture, but it's mostly methane, primarily methane, and it really depends on where the natural gas is. Different natural gases from different areas of the world have different concentrations, but here's a general idea here. And we take natural gas, we refine it, and then we send it out to businesses. Of course, natural gas here in Hawaii is blowover from our distillation column. It's not really natural gas. It's this leftover gases that are extracted from the petroleum. In general, natural gas has less sulfur, so it's the cleanest burning of all the fossil fuels. Methane itself is odorless, but we add chemicals, we add methyl mercaptan to it. That makes it smell really bad, and humans can detect it in a really small quantity. So that way we notice it so it doesn't become an explosive hazard. Coal's a little bit harder to deal because coal is a solid. And of the fossil fuels, natural gas and petroleum, not really sure at all. Actually, it looks like those are not fossil fuels at all. But coal, we're pretty sure is a fossil fuel because we found fossils in the coal. Back about 100 million years ago, the Earth was a lot warmer, the atmosphere was much thicker, and the Earth was covered in these big sort of ferny plants. And these big ferny plants, over the years, fossilize and turn into coal. And about half of the electricity that we have in the United States is made from coal. We get a little bit here on Oahu from pulverized coal. We get most of our electricity from petroleum. In general, though, with coal, the higher the carbon content, the more valuable the coal is. And I talked before about how coal can be liquefied. That's how Germany fought World War II, and that's also how South Africa gets their fuels. Here's our coal reserves. The state that has the largest coal reserve is Montana. Montana has the most coal. But you can see there's areas of the country like around the Appalachian Mountains. We mine quite a bit of coal there, and around Illinois region in the Midwest there, and quite a bit in the Rocky Mountains. There's Montana takes the cake by the most coal. We also have pretty high value coal. We have most of the world's supply of anthracite, the highest fuel value coal. So some problems with coal though. We get it out by strip mining, and this is tough on the environment. The strip mining means you take like a mountain, you either blow up the top of the mountain or you plow away the soil and the clay, and you get to a seam of coal there. And as the rainfall comes, this can lead to acid wash. Pyrite or fool's gold, iron sulfide, this isn't present naturally in the soil, and as the rainwater comes to it, it liberates some of that and makes the streams acidified. And there's also some trace elements like arsenic and mercury in coal. This has led to some bioaccumulation. We can't do anything about the natural sources of this, but we can do something about the anthropogenic sources, the human caused. And but these are easily captured. These now are being captured, and actually the amount of mercury and arsenic in the environment has gone way down the past couple of years, and more so than the anthropogenic sources have been. So the natural sources have been going down recently as well. In general, though, coal is a difficult fuel to transport because it's a solid. Petroleum and gas you can just throw into pipelines, but this stuff you actually have to put into trucks and or rail cars. It's a little bit harder to deal with. And some facts about coal: if you think that you do not burn coal, Where I told you here in Oahu we do a little bit, but if you're in Kauai or somewhere else and you feel like you don't burn coal, you do. Coal is really cheap electricity, and that's where they put a lot of the computer servers, are where there's cheap electricity. So whenever you order a book online, you burn coal because the servers are in the areas with the cheapest electricity. Every time a 2 megabytes of data are created, stored, and moved, that takes about a pound of coal. And because of this, the average internet user burns about 300 pounds of coal. And I must say, I do a little bit more than 12 hours per week on the internet, so I'm guilty of more coal than this. So it depends on your usage. The military is concerned about our fuel resources because the U.S. military is the single biggest consumer of fossil fuels. And of all the branches, the Air Force is the one that burns the most. And why? Because they have the most jets. And so they do quite a bit of research into this. And this is what the Air Force says, that of our resources, we have about over 2 trillion barrels equivalent of oil. So compared to Saudi Arabia having 260 billion barrels, there's quite a bit of oil that we have. And this does not include other sources of oil like offshore drilling. And there are billions of barrels, and also off the coast of California, there is a lot of oil in our country and around the world, and so we are not anywhere close to running out. With electricity, the way most electricity is formed is you have a wire, and then the generators work by taking magnets and spinning them around the wire. So that's how electricity is generated. And steam turbines usually turn the gear shafts that turn those magnets. Electricity is a very immediately useful source of energy. We use it primarily for climate control. The second biggest user is computers. The third biggest is appliances. Lighting tends to be less, but there is a lot of focus on lighting. The biggest usage is climate control. Consumes the most electricity. Computers are getting more and more. Why? Well, because we find computers everywhere. And our cell phones and our traffic lights, they're all over the place. And this is a typical coal plant, or any sort of combustion plant. You could substitute coal for petroleum. Natural gas, they can work off of a different way, where it has a rotary engine that it runs like a little tiny rocket or a jet, so it doesn't go through a steam turbine. But nuclear power plants work the same way, where the steam is generated, turns a turbine, then turns a generator. Generator is just magnets spinning around the wire. And where do we get our electricity here in the United States? About half from coal, a fifth from nuclear, a fifth from natural gas, and 10% in various other ways. So what are we going to do for the future? Our current source is fossil fuels as the primary. Eventually they're going to run out, or we're going to use it at the rate that before the earth can replenish it. Even the huge reserves that we have in the tar sands and oil shale. And so we need to have a new source of energy. Also, a new starting material for our chemical industry, because petroleum is the king. Everything runs on petroleum. Part of the problem, or part of the solution, is conservation. So we're fairly wasteful here in the United States of America. Also, gasoline can be served in the cars by various means. We can make appliances more efficient. Lighting, although it doesn't produce that much electricity, can be made more efficient. And not so much an issue here in Hawaii with insulation, but other areas that have more climate problems than we who are so fortunate on these islands. Insulation can be improved. A problem with improving insulation, though, is that can lead to radon gas forming in especially primarily the basements of some of these houses. So vents have to be installed. And don't have to worry too much about radon here in Hawaii because we don't have very much uranium in our soil. So where can we get other fuel sources? We already talked about nuclear fission in the chapter on nuclear power. Use breeder reactors. This is how nuclear weapons are made. They take at least plutonium nuclear weapons. take uranium and bombard it with a neutron to make plutonium-239. This is a nuclear fuel, and it's very powerful. And problem with this is that this is a way to make nuclear weapons. Part of the problem, though, fission alone will not solve our energy problems. We need more than just our current nuclear power plants. I went to a conference and I thought this was an interesting idea. Uh, People were talking there about combining nuclear power with coal plants because we do not run our nuclear power plants very hot. We don't like to have our nuclear reactors run very hot, not more than 500 degrees Celsius, which is cooler than a candle flame. But that still is hot enough to boil water. We use wet steam or saturated steam on our turbines. If we use coal uses superheat steam, which makes it a little more efficient. So the idea is we can combine the energy density of nuclear power with the ability to heat up the water a little bit more with a coal plant. And nuclear fusion, this is one of our two main choices. Solar is the other choice that we want to talk a little bit about, but nuclear fusion is one of the more attractive options. This is how the sun and other stars produce energy. And we can fuse deuterium, which is heavy hydrogen. We can find that from the ocean, and quite a bit of ocean water floating around. And the upside is with nuclear fusion, it produces more energy and with less radioactivity, so it's looking good, better and better. But the problem is we don't have the technology to have a surplus of power. We can make fusion happen, but we can't make it happen at a scale that it's energy positive, meaning we get more energy out of it, and we can't do it in a way that's very stable. And we have two type of fusion generators right now. We have the tokamak. This is a Russian design. It's basically a big particle accelerator that puts plasma and ionized gas together in a magnetic field. Or at the National Ignition Facility at Lawrence Livermore National Laboratory, they focus lasers down on a pellet. So the pellet explodes, what causes the center to implode and has a nuclear burn that way. Here's a picture of a tokamak fusion generator, and if you've ever seen tungsten carbide rings, you might recognize this color. Tungsten carbide is the inside of a fusion generator. Tungsten carbide is picked for this because it's a very sturdy material. It's very also does not respond that much to heat. And so this is a problem, though. If you have a tungsten carbide ring that's a very sturdy material, you can't cut through it. Well, you could with a diamond saw or a laser, but it would be very difficult. You could not use the jaws of life. That's what the like firefighters have. They can't cut it with the jaws of life. So if you catch your hand somewhere using a tungsten carbide ring, if you can't cut around the material, the paramedics may cut off your finger or your hand. So be very careful if you have one of those rings, because they're very sturdy materials. They're literally on the inside of fusion generators. Solar, this is the most attractive source of energy. Why? Well, the sun hits the earth with a lot of energy each day, about 1,300 watts per cubic meter, and that's a lot of energy. But less than a third of that actually reaches the surface, and it depends on where you're at on the earth, how much gets to. Obviously, in the winter time in the northern hemisphere, or in the northern or southern parts of the globe, there's going to be less energy. We get a little bit more here in the tropics. Solar heating, two types, passive and active. Everyone at some point in his or her life has done passive solar heating. If you've ever gone and sat out in the sun to warm up, that's passive solar heating. You're sitting there and letting the sun warm you. You're just doing nothing. Solar heating for water, that's called active solar heating, because you put energy in the system still. You use a pump to pump the water through. And here's a picture of solar heaters right there to the left. And to the right here, it shows a photovoltaic. And we'll talk a little bit about photovoltaic later. Photovoltaics directly turn light from the sun, or any light in that matter, into electricity. Problem with solar power is how clean it is. Actually, solar power turns out to be a little dirty. Solar power is becoming less and less popular As we'll talk about other types of alternative energies, it depends on where you're at. Here in Hawaii, it's what they've been finding out in general is it's not reliable at all. It's very it's inconsistent, and that's because we have cloud coverage, and the energy coming out from photovoltaics is inconsistent, and so that's why we burn a lot of oil here in Hawaii. We have to keep on burning oil even though we have a lot of solar panels up because the solar power just does not contribute all that much. And but problem with solar power, and we'll talk about this too with hybrid cars, there's a lot of environmental damage in making a solar panel. How do you make a solar panel? Well, they're made from silicon, so we take sand and we melt it. We melt it using coal, typically, because it's cheaper than petroleum, but you can use petroleum as well. Then we ultra purify the silicon, so we get metallurgy grade, then we get electronic grade silicon, and then finally the solar panel is assembled. And then the solar power is not consistent energy, and it's only during certain times of the day. The question is, do the environmental costs of making the solar panel and the energy and all the damage from the environment that we do to make the solar panel, is it justified in its use? So that's a open-ended question. It just depends. And hopefully as we get better at using solar power, getting different things other than silicon, then it'll be better. Solar panels work great out in outer space for satellites and whatnot. Solar panels work great. They get lots of there's the intensity of the sun up there is more than 3 times on average than the Earth. The sun is always shining. There's no atmospheric disturbances to cause inconsistency. So it's great up in space. Not nearly as useful to us here on Earth. We can get energy from biomass. Waste can be burned. We get a little bit of that. It's H-power here in Oahu. Also, biogas can be made from landfills. Same problem like most alternative energies. The biogas is not consistent. There's not a consistent output of product. Waste can be fermented to make ethanol. And the problem with ethanol is the energy negative process that it entails. So, meaning, if you look at a really narrow standpoint, just the distillation, you get a energy positive by a factor of 1.3 to 1, meaning if you put 1,000 joules in, you get 1,300 joules out. If you look at the energy, though, that you take by, so when you make corn, what do you have to do? Well, you have to plow the field, you have to plant the corn, you have to have the big turbines that spray the fertilizers and pesticides on it, and you have to automate it, and you have to take the turbines to pick the corn, then you got to transport it. As it's transporting, it's burning gasoline to the distillation columns, and if you look at all these processes, it turns out to be energy negative. Besides that, food crops are displaced, so we're taking food away from people to make fuel in an inefficient process. What other sources are there? Wind power. This is the main problem with wind power is it's not consistent. Wind power energy comes from wind is really not that useful at all, and that is the problem that wind power cannot overcome and probably never will. Geothermal energy. That's a little bit more promising than wind power. Problem with geothermal energy is that the reserves can cool, and then toxic materials can also be released. We're looking at using this more and more on the Big Island. Iceland uses quite a bit of geothermal energy. Geothermal energy was found in other places like San Francisco, but that was all used up. Also, water power. This is a very good source, but it causes environmental damage. It changes the ecology. Certain fish don't survive, and we use this in the Big Island of Hawaii. There's quite a bit of energy coming from that. Idaho has an interesting plan. Idaho has relatively inexpensive electricity. They burn coal all the time to have a baseline, and then hydropower is used for the peak power hours. A lot of politicians like talking about this, having a hydrogen economy, using hydrogen as a primary fuel. In general, hydrogen has a higher fuel value than gasoline, but it's also has some drawbacks. It has a poor energy to volume ratio, which means What's going to make you fatter? A cup of, or a quart, or a liter, whatever unit you want to have, a liter container full of popcorn, or a liter container full of olive oil? Well, obviously the olive oil will. So if you have a liter of gasoline and you have a liter of hydrogen, a liter of gasoline has more calories. And hydrogen's also explosive. It's extreme. So is gasoline, but it's not nearly as explosive as hydrogen, because when you get into car wrecks, usually they don't end up in a big Hollywood explosion. But cars that have hydrogen fuel would have that happen. Hydrogen is also used as a rocket fuel, to show you an example of how explosive it is. And electrolysis can be used if you add electricity to water. You can break it up into hydrogen and oxygen. And this is how people breathe on nuclear subs. If you wonder how a submarine can go underwater for 3 months or more at a time, it's because they take the water and their nuclear power, they have lots of energy there, and they turn it into, they break water apart into hydrogen and oxygen, they breathe the oxygen. And this though can help solve some of the problems that wind power and solar power have with their inconsistencies, is that they can be used to make hydrogen. So who cares if they're not consistent? And then we just use the hydrogen for other things. Fuel cells, we use these on spacecraft primarily. The space shuttle, before it was decommissioned, used a fuel cell, had a battery and a fuel cell. And this is a more efficient way to burn fuel. So for instance, a normal car, 25%, that's a pretty generous number actually. It might even be closer to 20%, but a fuel cell car would get about 60% efficiency. That's work per heat. If you compare that to the human body is about 33% efficient. So we get about a third of the energy available to work. So a fuel cell could potentially, you could argue, more efficient than the human body. But you need this though for hydrogen, because hydrogen has such weak energy per volume ratio, and this is really expensive right now. When I lived in California and Arnold Schwarzenegger was running for governor, he told everybody that he was going to switch his Humvee to fuel cells, and people thought it was a great idea. I was like, well, gee, thanks, Arnold. That's a slap across my face. You're telling me how many millions of dollars you have. For me, as a poor grad student, I didn't have that much money. I didn't even have a car. So really, it's expensive. Only the really rich and famous can afford fuel cell technology this time. But it's really interesting. I think the chemistry of this is really fascinating. You have hydrogen on one side and oxygen going in the other. Oxygen can just come straight from the air. And the hydrogen, what it does, it breaks apart and the electrons leave the hydrogen, does work. And then the hydrogens have to go through this kind of gel, and they go to the other side. And actually what they break apart in either platinum or palladium nanoparticles, similar to a catalytic converter. And they go through this gel, they go to another side where you have more nanoparticles, and then they react with oxygen on the surface. Water comes out. It's a I think the chemistry I think is fascinating, but as you can see, using platinum and or palladium makes it kind of expensive. A hybrid car really shouldn't be called a hybrid car, it should be called a dual car. A hybrid car has both a gasoline and an electrical engine. And this is a way to go a little bit further on gasoline, because you can use unused energy, like from braking, for instance, to store energy back into the electricity. And this helps things. So electrical cars have a very short range, not really any more than 100 miles is kind of the maximum that you could go on an electrical car. But gasoline cars on a single tank of gasoline, of course, can go more than 100, 200, 300 miles. And a hybrid car is the answer to have people that want to have more flexibility than just a 100-mile trip ability. And you can get really good fuel mileage out of this. But then again, there's the same problem with the solar panels. Does building a hybrid car justify the energy that you do to make a hybrid car? Because you're making two separate vehicles. You're making an electrical car and a gasoline car. Does that justify the environmental damage? Well, Where a hybrid car could be useful, actually here in Oahu, if you're stuck in traffic a lot, only buy a hybrid car if you're stuck in traffic a lot, and or if the air quality is really bad. So if you're stuck in traffic a lot, live in LA or Mexico City, that's a good place to have a hybrid car. If you drive a hybrid car long distances all the time, you actually get less fuel value than a normal engine. Hybrid cars weigh more. They weigh about 10% more because they have two different types of propulsion systems. And the other thing about hybrid cars is they have a lot of them don't have steel frames, so they're a little bit more dangerous if you're in a car accident with a hybrid car. If you live in the country, so if you live in the Big Island and or in the country in the continental United States, and you drive long distances without traffic, you are actually doing the environment more harm than good with a hybrid car. You should get a normal gasoline car engine. So only have a hybrid car if you have a high traffic situation and or the air quality is really poor.